Hello, welcome back to more about sequences. So in the last few videos, we've talked about what a sequence is, that a sequence is a list. That was a major idea. And we've spent a long time talking about how to find limits of sequences. But one of the things we need to talk about before we wrap things up here is several important definitions and a theorem or two about sequences. So mathematicians are, well, we're funny about our definitions. This is what separates math from lots of other disciplines. Is mathematicians will start out a paper they've written or something they've worked on, and they will make definitions. They'll say, I'm going to use the word increasing, and when I do, I mean this thing by it. And then another mathematician might think it's a stupid use of the word, but they don't argue over whether or not that's true or not. They just, accept, okay, he's using the word increasing to mean this, and from now on, when I see the word increasing, I'll know that's what he means. Again, they may think it's silly or stupid, but nobody argues over whether or not a definition is right. So in this example, right, this case here, we're going to use the word increasing to mean the following. A sequence is increasing if every time if the next term is always bigger than or equal to the current term. Maybe that's the easiest way to say that. To be really precise, right, then whenever you have an n, a sub n plus 1 will be bigger than or equal to a sub n. So for example, a sub 2 will be bigger than or equal to a sub 1. A sub 3 will be bigger than or equal to a sub 2. A sub 4 will be bigger than or equal to a sub 3 for every n. So every time the next term is bigger than or equal to the current term. That's one way to say this. Right? You may think it's a little weird to use bigger than or equal to since I'm calling this increasing. And not every textbook does it that way. So remember I said that mathematicians will sometimes say you're using a silly word, and they do. But, so here's a place where some people will use a different word. We're always going to use the word increasing right here to mean bigger than or equal to. Some books will use the word non-decreasing to mean what I've written here. Bigger than a sub n plus 1 is bigger than or equal to a sub n. I don't like that because the truth is, when my brain sees non-decreasing, the part that my brain fixates on is the decreasing part, right? And so saying it doesn't get smaller, well, that's true, but all I hear is the smaller, right? It's sort of like I hate no left turn and no right turn signals. The big arrow that points to the right and then a slash through it. When I see that, all my brain sees is the big arrow, and it's like 3 beats later before I see the big slash through it and recognize, oh wait, this is telling me not to go that way. So okay, so whether your brain works that way or not, what we will always mean when we say increasing is that a sequence is the next term is bigger than or equal to the current term for every n. Okay? If we need to be more specific, and I mean bigger than, we'll call that strictly increasing. Okay, so it's worth pausing and talking about some examples. So suppose I have this as an example. Suppose I had a sequence that was like n. So in other words, 1, 2, 3, 4, 5, 6, 7, 8. That would count as strictly increasing because every term is definitely bigger than the one that came before. Right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. It would also count as increasing because every term is bigger than or equal to. In fact, it's bigger than means that it still counts as bigger than or equal to for every n. Okay? But suppose I had a sequence like this: 1, 2, 3, 4, 5, 4, 3, 2, 1, 1, 2, 3, 4, 5. Okay. You wouldn't say that it increased part of the time and decreased part of the time, because notice that it says here this has to happen for every n. So this isn't like those problems in calculus 1 where we would say we had a function and it was increasing here and it was decreasing here, so we had a maximum, minimum, blah blah blah. It's not that. We're using this word in a completely different way. When I say that something is increasing, a sequence is increasing. When I say a sequence is increasing, it means that every term, right, is bigger. Every term, the next term is bigger than or equal to the current term. I should say that again. When I say a sequence is increasing, I mean that a sub n plus 1 is bigger than or equal to a sub n, no matter what the n is. Okay? It's always getting bigger than or equal to the one that came before. And a strictly increasing sequence, the next term has to definitely be bigger than the one that came before. Okay? Always. It can't go up and come back down and still count as increasing. Okay? But there is something else that's a little weird here. Right? Think about a sequence like this: 7, 7, 7, 7, 7, 7, 7, etc. It's a really boring sequence. Is it increasing? Well, maybe you think it might not ought to be because it doesn't actually get bigger, but look at our definition, right? Every term has to be bigger than or equal to the one that came before. Bigger than or equal to. So a sequence that's a constant, like 7, 7, 7, 7, 7, 7, 7, that counts as increasing. It doesn't count as strictly increasing, but a constant sequence like 7, 7, 7, 7, 7, 7, 7 definitely counts as increasing. In fact, it also counts as decreasing. So if you have a sequence where the next term is less than or equal to the current term for every n, that would count as decreasing. So it is possible to have a sequence which is both increasing and decreasing, but the only way that can happen is if it were a constant sequence where every term equals the one that comes after it. If I need strictly decreasing, well, I'll do that the same way, right? Every term has to be definitely smaller than the one that came before. So can you have a sequence which is strictly increasing and strictly decreasing? Well, no, that can't happen. So you could have a sequence which was both increasing and decreasing. Both of those things could happen for the same sequence, but it'd have to be constant. You could not have a sequence which was decreasing and strictly increasing, right? Those don't work together at the same time, okay? For the same sequence, I should say. Okay, okay, well, what if I want to have kind of a generic word, right? So we're used to sort of generic words, right? Where I come from, you will often hear people go up and say, "I need to order a Coke. Give me a large Dr. Pepper," right? Because we use the word Coke to mean a fizzy brown beverage, not necessarily something that's made by Coca-Cola. Uh, so it's the same sort of thing here, right? We want a word that's slightly more generic. And so here's one, right? We call a sequence monotone, not if it's boring. That's not what that means. A sequence is monotone if it's either increasing or if it's decreasing. So suppose you have a sequence which is increasing, then it counts as monotone. Okay? If you have a sequence which is decreasing, it would count as monotone. If you had a sequence which was strictly decreasing, that would also count as decreasing, right? Because decreasing means less than or equal to in the terms. So if it was strictly decreasing, that would also count as decreasing. That would also count as monotone. Want to see how that works? Well, another set of definitions. Right? A sequence is bounded above by some number, call it m, if every term is less than or equal to m. Okay? So suppose that you had a sequence like, I don't know, say 6.9, 6.99, 6.999, 6.9999999, etc. See where I'm going with that? That sequence is obviously bounded above, right? Because in fact, it's obvious what the limit is. Those numbers, the sequence is definitely getting closer and closer to 7. They never get bigger than 7, right? So that would be an example of a sequence bounded above by 7. Now, technically, that sequence that I said would also be bounded above by 8 because the sequence never gets bigger than 8. They never got bigger than 7 for sure, but also never got bigger than 8. Right? It'd be bounded above by 10 million too. Maybe that's not very helpful to know, but a sequence is bounded above by m if all the terms are less than or equal to m. And bounded below works the same way, right? A sequence is bounded below by m if all the terms are bigger than or equal to m. Okay? Right? Now, remember, monotone was a generic word, right? Increasing would count as monotone, decreasing would count as monotone. Bounded is a different kind of thing. To be bounded, it's actually more specific. Bounded means it's bounded both above and below. So suppose you have a sequence which is bounded above but not below, then it's not bounded. Okay? Again, you may think the words are weird to pick to mean what they mean, but once we've decided on what the words mean, this is how we're going to use them. Okay? I'll give you an example. Suppose that you have a sequence like this. Um, say, say 0, -1, -2, -3, -4, -5, and so on. That's definitely a strictly decreasing sequence, right? It's going down every time. It's bounded above by, well, by 0, also by 2 and 3 and 7 and 15 million, right? All those are numbers that are bigger than the sequence that I just said. It's bounded above. It's not bounded below because it keeps getting smaller and smaller and smaller. It's not bounded below. Okay? The bounded monotone convergence theorem is stated in our textbook, but actually it's stated slightly differently. So I'm going to state it in 3 parts. I think it makes a lot more sense when you say it in all 3 parts. It's stated in the textbook only the last way I say it here. Here's the deal. An increasing sequence converges if and only if it's bounded above. Okay, what? Let's just break this down and see if we understand what this means. Suppose I had an increasing sequence. So the numbers keep getting bigger than or equal to each time. Bigger than or equal to each time. Well, how could something like that converge, right? I mean, it may be that my sequence looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It doesn't converge, right? But of course, a sequence like I just said isn't bounded above. It just keeps getting bigger. Oh, well, that's the deal. An increasing sequence that converges has to be something like the example I said that was like 6.9, 6.99, 6.999, 6.99999. It's increasing, keeps getting bigger than or equal to every time. But it's bounded above. It never gets any bigger than some value. And of course, that smallest upper bound is what it's actually converging to. Same thing, but in reverse, for a decreasing sequence. A decreasing sequence will converge if and only if it's bounded below. Because if you have a decreasing sequence, if it just keeps decreasing forever, it's not going to converge. But if it runs into something and it doesn't go past it, then it'll converge. Okay? The way our textbook states this theorem is it sort of combines these two and says a monotone sequence converges if and only if it's bounded. So remember, monotone means, well, increasing or decreasing, one or the other. I don't know which one it is. Could be one, could be the other. And a monotone sequence, say it was increasing, right? Then it'll converge if it's bounded above. If the monotone sequence was decreasing, it'd converge if it was bounded below. So that generic word monotone, right, would be one or the other. Well, in order to make sure it converges, we need it to be bounded, period, which means bounded both above and below. Okay? So in a lot of ways, what we've just talked about is, well, it's what mathematicians do. It's playing with words, right? It's trying to keep all these words straight in our head. This is not a hugely important, say, part of the next exam, but there may be a question or two about this. So thinking through the definitions, reading the PDF file about that lists these out, and thinking through how this would happen is kind of important. And we can talk more about this in the discussion board. Um, Here's another thought to think about for a second as you stare at this theorem. Suppose that I had an increasing sequence. Okay? Does it have to be bounded below? Think about that for a second. Increasing sequence. Is it always bounded below? Well, yeah, because it keeps getting bigger, right? Bigger than or equal to every time. And so what's the smallest thing in the sequence? The first term. So the smallest term in the sequence is the very first one, which means that whatever that first term is, that's as small as it gets. So that would count as a bound below for that sequence. Okay? So asking yourself questions like that is a useful preparation for thinking through these terms. So how in the world would this show up on an exam, right? This is not exactly a problem to work out, like find this limit or something. The typical thing you'd ask on an exam is, is maybe a true-false question, right? Or ask this as, suppose that you have a decreasing sequence. Does it have to be bounded above? The answer is yes, because if it's a decreasing sequence, right, the biggest term in the sequence is the first one. So it never gets any bigger than that first term. So it will be bounded above. Is it bounded below? Well, if and only if it converges. So this kind of thing gets asked, especially that you'll see in the homework, as explain or as true, false, or so forth. Not so much as compute a number or an answer. Um, this is a really, really good practice for starting to learn to think the way that mathematicians think.